All right. So, 8H today, and this is a bad lesson to get away from. This is going to be a little bit challenging, but we'll work through it slowly. We'll go through both examples. It's a good skill, it's a complex skill, and it's one that's pretty prevalent in a lot of the past exams that I've had a look at. So the first thing I want to point out is just a type of function, and that's the logistic model. So you're given the information about this, all right, in the notes booklet there. This is a logistic function. And what a logistic function is it can be used to model some sort of growth where it has some limiting factor or some decay as well. We can have decay in the logistic sense of the word. And so we use this you'll see this in calculus, right, when we're modelling the height of a tree. Okay, a tree sort of reaches a certain height and it gets closer and closer to a certain point, but it never sort of improves any taller, really. Populations tend to do this because they reach a point where they can't grow anymore and so forth. So this is a logistic function, and there's some properties of it listed there. Okay, then down along the side here, we've got a proof for the integral of the logistic function and how it's performed. So that's the general circumstance. We're going to look at a couple of specific cases. And then on the right, they've got a clever rearrangement there that you may be using on this exercise. Okay, so keep that substitution in mind. Excellent. Let's get straight into the question then. We have the rate of population growth since the year 2000 can be modelled by this equation. 12.5. And part A says, show that 12.5 on n times 12.5 take n is equal to 1 on n plus 1 on 12.5 take n. Okay, so let's start with the right-hand side. Right-hand side. We'll write it out, and we'll perform this by cross-multiplying the denominators. And then simplifying. N times 12.5 take n. Alright, which is the left-hand side. Okay, so we've started with the right, we've manipulated it, and we've got the left. Okay, so this here is where the real skill sort of comes into it. We have hence solved the differential equation to show that n is this. Okay, given some initial piece of information. So I want us to solve this equation. This is going to be using skills we've sort of looked at and a number of things. So I'm going to write the equation up here, and then we're going to start to try and solve it. Okay, so the first thing I'm going to do is I'm going to multiply both sides by 12.5, and then divide both sides by n times 12.5 take n. So what that's going to do, I'm going to shift that term over here. This dn or dt remains. And the only thing left over there is 0.002. So I've done a couple of things there. This is sort of the level of detail you'll have when you're performing it. So we're starting with that, okay, and times both sides by 12.5. Sorry, I should 12.5 on the top. And then divide both sides by this part. N times 12.5 take n. So it cancels it here, brings it over there. Excellent. And what we've got is we've got everything affiliated with n on the left, and then we've just got this number on the right. Now before we integrate it, we're going to put it in a form that we're able to integrate with. And remember, we've said anytime there's a show that, it means you should probably be using it. So the first thing we're going to do is we're going to perform the substitution here that we showed is true over here. So we're going to, here we've got this statement, we can't integrate that, but we do know it can be written like that. So let's substitute it, and then that's the one we're going to integrate. So what we have is we have 1 on n plus 1 on 12.5 take n, and that's dn on dt. Equals 0.32. Okay, so that's a link. We know that it can be written in that form. Okay. Next, we will integrate both sides with respect to t. So this one goes to ln modulus of n, and then we're going to have to take away ln modulus of 12.5 take n. Alright, take away because it's 1 on top of the coefficient of n. Integration there. Over here, 0.02t plus c plus our constant. And what we're going to do is we're just going to process this to solve it for n. We're going to isolate n. So, first I'm going to collect these logarithms together. Now, I'm forgetting a 0 in some of these. That's 0. Okay, we'll put e to the power of both sides. So I'm going to jump straight to here. Next, what we're going to do is we're going to flip both sides, okay? And I'll show you the reason why we're going to do that in a moment. This will generally be the case when we have a logistic function that we're trying to separate. So what I'm going to do is I'm going to flip this denominator. I'm putting both sides to the power of -1, right? That's technically what I'm doing, okay? So we're putting -1 and then to the power of -1. And so what that does is it flips the denominator, right? So we have 12.5 take n at the top and n at the bottom. And then over here, well, the -1 can just distribute. We've got plus or minus e to the minus c, and then e to the minus 0.002 t. Okay, we'll substitute plus or minus e to the c as a, just to clean up our notation a bit. And this is the reason why we flip it. Alright, is we want to split the denominator. We can't split it when it's two terms, we can split it when it's a single term. So we're going to express it like this, 12.5 on top of n, take n on top of n, equals a e to the minus 0.002t. Alright, so we're substituting that for e to the negative c. We've split it. And why this is useful is here we're going to have n divided by n, which is 1. And so then we've isolated it down to n by itself, which is what we're trying to solve. So I'm going to come up here, and what we've got is we've got 12.5 on top of n equals, 12.5 on top of n, take 1, equals a e to the minus 0.002t. Okay, add 1 to both sides. And then we're going to swap the n with the a, right? So we're going to have n equals 12.5 on top of a e to the minus 0.002t. Okay, so we're most of the way there. There's one small step left to do. Okay, so we've got, with the context of the problem, this is the rate of population growth since the year 2000. N is the population of the world in billions. When t is 0, so that's years since 2000, when t is 0, the population is 6.08. So what that means, we can substitute that in here. T is 0, N is 6.08 billion. Alright, so let's perform that substitution. Now, I forgot plus 1 here, sorry. So when we take 1, we have to add it to both sides. So that is plus 1, that is plus 1. And then we get it here. Sorry. Plus 1, below the denominator. And here, a plus 1. Okay, so then we get a plus 1. And then we subtract 1, and we get a equals 1.06. Okay, so a is 1.06, therefore we can write n as 12.5. As required pretty nasty sort of long-winded problem. These are sort of 5 or 6 mark questions in the exam. In the test will be the same. So just a quick recap of what we did. Alright, we start with the differential equation, we isolate the n parts of it, we're leaving that number over there. We know that that can be written in this form. We split it, we perform the integral of both sides, we combine those ln's, we apply e to both sides, okay, and then we apply -1 to both sides to flip it so that we can split the denominator. We've performed the substitution for a here, we've split the denominator, we're still processing it. We've isolated n at this part by itself. We perform that substitution to solve for a. We've got the a value, so this is the equation of n. Alright, so it's a fair bit going on there, yeah? So we've got the equation, and now we're going to use the equation to answer these questions. So the first one says, according to the model, in what year is the population growing at the fastest rate? So there's 2 ways you can answer this. Okay? And we're going to use that calculator, right? The first way is, this is the rate of change function. So you could graph that g sub the max, what's the time value associated with it? Because that's what it's asking, what's the time value? The other way we could do it is we could graph this function, okay, which is the logistic function that describes the population of the Earth. Alright, and so that's going to look something like that. Alright, and it says, when is it growing at the fastest rate? Okay. Now, if you look at the information about logistic functions there, they tell you there's always a point of inflection at y equals c on 2. Now, that's useful because that tells you that's when it's growing at the fastest rate, when the y value is 12.5 divided by 2. Right? Because c, if you look, corresponds to 12.5 in the logistic function. So if we go 12.5 on 2, we've got, it's when y is 6.25. So that's the population, but we still need the corresponding time value. So we're doing an x count when y is 6.25. Alright, so they're the 2 ways I would encourage you to answer that, either from the derivative function or from the function that we've solved for. So I'll quickly go ahead and get that one. Unless anyone's got it already. Minus 0.002x. I'm not seeing the solution here. I'm just going to change the view window a bit. Okay. Trace g sub x count y is 6.5. And I've got x is 69. So time is 69. Where am I going to answer that? Let's go here. So this is for part C. T equals 69 years after the year 2000. So what year is that going to be? 2069. And that's pretty accurate based on current predictions. Alright, the population is supposed to peak, and it is supposed to peak about 12.5 billion. Between 10 and 12.5 billion. Okay, according to the model, yeah, that part's answered. And then what's the limiting value of the world's population? Okay, that's 12.5 million. Okay, and we know that's the limiting value because that's the number that exists at the top here. That's always going to be as high as the graph can possibly go. Alright, so any questions about that one? Cool, I'll clear the board and we'll get on to the next one. Oh no. Someone's put spray on the board. Look at the difference. Okay, so it's going to follow a pretty similar process, but it gets a bit harder towards the end, this one. So we have a species of animals in danger of extinction. The rate of change of the population is given by dy on dt is equal to minus 0.1 y times t take y on top of t. Okay, where t is time in years after the population y was initially counted. Capital T is some constant, and the constant capital T is the threshold level of the population. The species will become extinct if the population falls below capital T. Part A, show that. So I'm going to start with the right hand side. I'm just going to jump straight to it. 1 on T take y. Now remember I've said when we're asked these show that's demonstrate all the steps clearly. So cross multiplication. Start left hand side, right hand side equals the left hand side. Cool. Part B. The initial population is 20,000 animals. Show that the population of animals is given by this equation. So we need to start with this differential equation, and we're going to solve it for y. Okay, we want to isolate y in terms of t. So what we're going to have. We're going to leave this point 1 over here and move all of these things over this side. So we're going to have at the top, like here's what I'm doing. I'm going to multiply both sides by t to start with. We've got t at the top, and then I'm going to divide both sides by y times t take 1. So then we have that at the bottom. And then we've got the dy and dt. And we've got left over here minus 0.1. Alright. Now, pretty similar process to what we were doing. Because we've performed this show that, and we need to split it into these components. Perform the integral with regards to t. Alright, and I'll go through this part. We're going at an okay pace. Don't go too quick. So again, combine the integrals. ln A take ln B is ln A on top of B. Minus 0.t plus c. Put e to the power of both sides. So we'll have, and I'm going to perform the A substitution straight away here. A e to the minus 0.1 t. Alright, we're going to flip both sides. We're putting both sides to the power of minus 1. That might be like this stuff here. So we'll have here t take y on top of y equals a e to the power of 0.1 t. Alright, so we'll put it to the power of minus 1. It's going to change it from the negative to the positive. Split the denominator on the left hand side. Come up here. So we've got t on y, take y on y. So we've isolated y. And we have the initial population is 20,000. So it wants us to show that it can be written in this form. So I might come up here. So we've got
to the plus 1.
Yeah, geez. So where did I miss that out?
Show that, yeah.
Should be plus 1. And it's at the denominator, it's plus 1. Yeah, very important, thank you. Alright, so we've got when time is 0, y equals 20,000. Right, so that's the substitution form. Equals. Okay, so here let's just solve for A. Here this part, right, with this last part, you're not exactly sure how you want to get to the equation that they've got. There's a number of ways to get there, so you just wrestle with it until you get something that, until you get the same thing they've got. So there's a number of routes you can take. Here's what I'm going to do. I'm going to solve for A and then substitute it back into the problem we know. So we've got here A plus 1 equals T on 20,000. And then I'll subtract 1. So we've got A equals T on 20,000. Take away 1. Okay, so I've got a value of A, and I'm going to perform that substitution into this equation here. Alright, so if I perform that substitution, we're going to have Y equals T on top of, we've got, here's the A value, positive 0.12. Alright, so we've substituted the A value there, and we're reasonably close. And all we need to do, if you're looking at that, we've got 20,000 at the top. If we multiply it by 20,000 on top of 20,000, okay, so we're multiplying it by 1, we're not changing its value, right? At the top, I'm going to have the 20,000 T, and at the bottom, okay, this is going to distribute. So firstly, we're going to have the plus 20,000 there, that's what we need, so that's good. And then it distributes into this bracket as well. So we're going to have e to the 0.1t, we've got here take 20,000, and here, when we distribute it there, we're just left with the t. Okay, so that's exactly what we're after. Alright, so with that last part, just a bit of wrestling with it until you get the same as what they're after you to have. Okay. Next part says, find the threshold value t, given after 50 years, the population is 5,000 animals. Okay, so what this means is when t is 50, after 50 years, y is 5,000. So we're going to substitute that into here. Okay, and what we'll have is we'll have 5,000 equals 20,000 t on top of t take 20,000 e to the power of 50 times 0.15 plus 20,000. Okay, we're going to put that, we can graph that and g-solve the x value or the t value when it equals 5,000, or you can put it in equation solver. What's the variable we're after? We're after t. So I thought I'd written it down. Hopefully I've got it here. Crank the V window right out. Okay, so I want to know the x value when y is 20 minus 5,000. And I've got 20,415. Okay, so we've got the t value. Alright, so now that we've got the t value, we can process this a little bit more to get the equation exactly as it stands. And then part D, right, says draw the solution to the slope field, okay? So here, even if you haven't got the previous parts, you can still graph this. Well, firstly, they do give you the equation. And secondly, you're given the points that it goes through. So the first point that it goes through is time is 0, population 20,000. And then the second point it goes through is time is 50 and population is 5,000. So you just have to make sure you draw the slope field that goes through those points. So it's looking something like this, isn't it? Okay, so this is an example of a logistic function that decays, all right, decays towards some limiting value. Population can't drop below 0. All right. So it's pretty tricky one, but it's good fun. They're sort of long problems.